Hello and welcome to another video for Reigate Maths. This is Simon and today we're continuing in our series of videos on the application of forces, part of the second year mechanics content. In this video we are looking at several examples of connected particles. We'll focus on doing one full example, but we'll talk about other ways that these can come up. So what do we mean by connected particles? Well, it's in the name. Any two particles that are connected by some form of string, whether it's two particles hanging and looped over a pulley, maybe this is a bucket and this is a weight that you're using to pull the bucket up. We might have a particle on a surface, whether the surface is at an angle or flat, doesn't change a huge amount in terms of the concept. Obviously it changes the maths, but there we go. Again, looped over a pulley with another one hanging. Or we might have a situation like this where we have a car pulling a trailer, for example, connected by a tow rope or something like that. Or it might be two train carriages connected by a coupling. The key thing with these is in all of them we have tension because there are strings or there are sort of other string-like things. Tension is always in two directions, but generally we only worry about one of them. The direction that is opposing weight, or in this case opposing potentially motion or opposing a backwards force. So in this case we'd be worrying about the tension here and here. And here we'd be worrying about the tensions in either side, like that. Now in this case, very typically you will consider one of the particles or maybe the other one, depending on what you're trying to work out. But if we don't know the tension here and we're trying to work it, or we're either trying to work it out, in which case we do one of these things, or we just want to ignore it entirely, we would consider the whole thing as one giant particle, because the tensions are the same, so they cancel out. In these two cases, we can't do that, because the particles are not going in the same direction. Even if these two particles are pulling against each other, it's still the same idea. Here, these particles are not moving in tandem like this. This one's moving down, or potentially up, and this one's moving along the plane. Likewise here, these ones are moving up and down. In this case, we must consider each particle separately. We cannot do like we might do here and consider them as one big thing. Likewise here, we must consider each particle separately. So what we're going to do is we're going to look at this type of question, because this is the most complicated type of connected particles question you can get. So if you can follow this, you're sorted. So here's our diagram. We have two particles, P and Q, attached by a light inextensible string. The string passes over a small smooth pulley, which is fixed at the top of a rough inclined plane. So lots of assumption words there. Light inextensible string, so the string doesn't have any mass and it doesn't stretch. Smooth pulley, so it doesn't have any friction in it. This pulley is also small, which means that the size of the pulley is irrelevant. And then the plane is rough, so it means there's friction. P rests on the plane and Q hangs over the edge with the string vertical and taut. It's important that the string is taut because it means everything's just going to move immediately when it's released from rest. The plane is inclined at an angle where tan alpha is 0.75. If you've watched the previous video on applications of forces, that should be familiar. And the coefficient of friction between P and the plane is 0.2. The system is released from rest and we want to find the acceleration and then find the tension. So, as very typical with questions like this, let's label our diagram. Let's look at Q first because it's nice and easy. What are the forces acting on Q? Well, obviously there's its weight, 10 times g, and then there's tension. There are no other forces acting at Q. There are other tensions up here, but they're not going to be important for this question. Now let's look at P. Well, we know there's a weight, and we know that that's going to be resolved into a triangle like we saw before. Because it's resting on the surface, we have a reaction force. We have a tension that's going to pull the box P up, and we have a friction. How do I know the friction goes this way? Well, Q is heavier than P, so Q is going to accelerate down. Which means P is going to accelerate up. So P is going to move this way, which means friction goes the other way. Now, how do I know that these accelerations are the same and these tensions are the same? It's because the string is light and inextensible. Okay. So this is now everything labelled that we need to answer the question or to find the acceleration. What we are going to do, and the way these questions will very, very typically work, is resolve forces for Q, or do F equals ma for Q, F equals ma for P, and then simultaneous equations of some description. So let's do Q first, because again, there's less going on. It's a bit easier. So resolve at Q. So we know F equals ma. So it's moving down, so the 10G is bigger than the tension. So the resultant force is 10G minus T, and we know that's going to be equal to mass times the acceleration. Nothing else we can do with Q. That's everything there. We're now going to resolve at P. P gets a little messier, which is to be expected. There's a lot more forces going on. So let's have a think. Which force is the biggest? Well, it's moving this way, so tension is the bigger force. So we know tension minus. What are the forces going the other way? Well, one of them is friction, and the other is this component of the weight, which we know is 5G sine alpha, because it's opposite. And we know that's going to be equal to 5 times A. Well, let's do some tidying up here. So we know that friction is mu times R. R is going to be 5G cos alpha, and we know mu is 0.2. It's 0.2 times 5 is 1, so we just get G cos alpha. Much like before, we can use a triangle to work out what cos alpha is. I'm just going to do that up here. Alpha, we know tan alpha is 3 over 4. Don't be fooled by the fact that it's a decimal. Write it as a fraction, it'll work. So opposite over adjacent, which means our hypotenuse is 5. So our friction is 4 over 5G. We can now start putting things in here. So we know that T minus friction, 4 over 5G, plus 5G times sine alpha, which is 3 over 5, is going to be equal to 5A. So T minus 4 over 5 plus 3 over 5 times 5, so 4 over 5 plus 3. So 19 over 5 G equals 5A. And this is equation 2. Part A of this question is find the acceleration. So we need to eliminate T from these, very simply by adding equations 1 and 2 together. If we do that, we get 10g minus 19 over 5g is 15a. So 15a is 10 minus 19 over 5, 31 over 5 times by 9.8. So 31 over 5 times 9.8, which is 60.76. So A is that divided by 15, which is 4.05 meters per second squared. Part B of the question is just going to be substituting it back into A to find the tension. And you can see the answer here, 57.5 newtons. Now there's a lot more additional stuff that can happen. You could be asked to find the tension or the force, resultant force at this point, which is to do with the fact that we have tension, other tensions going here and here in the opposite directions. So the string is pulling down in two directions, so the resultant force will be somewhere in the middle. And that kind of thing. But in terms of the actual kind of process of finding the tension and acceleration of connected particles in this way, we're done. Now if we had one of these examples again, it's very, very similar to this example we just did, but much, much easier because we have fewer forces here. We don't have a reaction force because this particle's not sitting on anything. We don't have a friction because it's not on a surface. The weight is not at, we don't have to worry about resolving the weight because it's in the direction of motion. So for questions like this, we don't have to worry about nonsense here. We just get two versions of what we did at Q. One where the tension is second, one where the tension is first. Because unless the particles are exactly the same mass, they're going to move. Well, one's going to move up, one's going to move down. So if you can get your head around this example, this is pretty much as difficult as it can get, where you start to involve friction, as well as lots and lots of forces. Other things they could do, much like in the previous video, we've found an acceleration, so they could do SUVAT. We're kind of here. They could do SUVAT and then say, oh, this now hits the pulley and the string snaps. What happens here? And you've got to think about, well, now my acceleration is different, but my initial velocity I can calculate, that kind of thing. So there's lots that they can do in and around this type of question involving SUVAT. But I'll let you practice those when you get to them. Thanks for watching.